Hello, everyone. I'm Chinar, the CEO of Manot. Manot is an insight management platform that helps you to analyze AI performance and behavior. We propose actionable insights in the form of images where your AI model could fail. Today, we will explore how generative AI can identify blind spots in AI models. Whether you are working on the product side or the development side of building and delivering AI models, during this session, we will cover several key areas. We will review the ML lifecycle, look deeper into the gaps of the current state of monitoring, observability, and explainability, talk about generative AI as a solution bridging this gap, and by the end of it, I'll walk you through our platform, its core features, and will showcase the benefits on an example. Picturing a world where AI is not just a lab experiment, but a daily companion, working wonders in our lives isn't far off. Think about your home becoming smarter than ever. Lights, temperature, and even your coffee maker know how you want before you do. Imagine cars that drive themselves, avoiding traffic and accidents with ease, and in stores, AI makes sure everything is stocked just right so you never run out of your favorite snacks. But like any adventure, there are twists and turns. Remember the time when Tesla was mistaking the moon for a traffic light? It sounds funny, but it could have been dangerous. With the deployment of computer vision in airports, self-driving cars, grocery stores, and home security systems, such hiccups are unacceptable. They remind us that AI, while powerful, needs careful handling. As the technology matures, a different class of security issues arises, and the question remains, how do we generalize a computer vision model to new regions and novel environments so that it never fails to distinguish between, say, a traffic light and the moon? To get to the solution, first, we will have to understand the problem. Neither Tesla nor any other company is able to avoid AI model failures. Let's say misclassification, misdetection, false positives, or false negatives. As there is always a huge gap between the training data and the real-world scenarios. Any training data is always limited and doesn't represent the outside world, as the world constantly changes and evolves over time. Right now, the overall ML lifecycle is the following: collect data, prepare it, train a model, evaluate it, deploy it to production, and only then get feedback about its performance in the production environment and repeat the cycle. And 70% of AI models that go to production show that there is a long feedback loop to identify failures, report it to the development side, and resolve it. This means in the ML lifecycle, the long feedback loop is between the product and development sides, and it takes months to refine and redeploy more accurate model. We surveyed more than 150 companies to clearly lay out the feedback loop flow. First, they identify failures. This means either wait for product managers to tell us something is wrong with the model, or use proxy signals or heuristics to approximate errors. At the very least, embrace a certain number of silent failures as an acceptable risk. Then they diagnose failures by manually analyzing the failure reports, manually classifying and labeling reporting failures, and sometimes reproducing them. Lastly, manually ranking and prioritizing. Finally, this results in refinement cycles stretching from 2 to 4 months, involving unhappy customers or end users and stressed out product managers. Today, the current solutions focus on model performance degradation using well-known techniques like monitoring, observability, and explainability. And if you talk in more detail about the pros and cons of each, those will sound like this. Monitoring, which is KPI based, follows some rules and provides heuristic alerts. It doesn't describe failures. It just shows that something dipped below a threshold somewhere. Observability describes data drift, meaning changes in production data distributions and statistical generalizations, but it doesn't tell you what the error is, what to target, and how important is it to model performance. And finally, explainability helps you understand predictions, but not false negatives. It doesn't tell you why it didn't detect the car in the background under the tree. And all of these are dev tools. And mainly technical people, data scientists, data engineers, computer vision engineers use them. For that reason, these tools are highly specialized from the model development angle. And now, what is the gap? All of these mentioned solutions do not cover the most important gap, a continuous feedback loop with actionable insights on the model's potential failures, without any heuristic, deterministic rules or categories. The practice and experiments show that the deterministic approach fails, missing crucial test cases and unexpected scenarios where the model fails really badly. Remember the Tesla moon example? Lastly, a part of the solution relies on the trained model itself, meaning the trained model that could potentially fail is being diagnosed against itself. Practitioners diagnose the performance just by manually checking the output or defining thresholds or unit tests. Lastly, the mentioned solutions do not try to reveal potential false negatives, which we call unknown unknowns. If we simplify this overall problem and existing solutions with the missing key points, it will be the following. We will get this. There is a gap between the product and development side, and a tool that could cover both sides' needs. Automated continuous feedback loop from product side to development side. Actionable insights into potential failures and performance degradation by just looking at the test set, a subset of images, and the model performance only on it. In order to complete and connect the mentioned problems in the model monitoring, observability, and explainability space, we propose proactive analysis and diagnosis of model performance through an actionable insight management platform. The unique value proposition of the shown flow chart is the following. First, you get an automated continuous feedback loop about model performance without deterministic or heuristic test cases. And you are always informed where the model could potentially fail, including false positives and false negatives, those unknown unknowns. And most importantly, you get to work with a platform that is designed both for product and development teams. Manot pulls actionable insights in the form of images, either from its large data lake or generates it for you. From the beginning of this session up to this point, you have probably heard me say the term actionable insight at least seven times. So it is high time to understand what this means. So actionable insight comes in the form of an image that potentially contains false positive or false negative for your model. For example, misclassification, misdetection. It also has a failure importance score attached to it. Higher score indicates worse performance. With the image, you will get a description of the failure. For example, people walking, backs to the camera, wearing glasses, and many more. And finally, for the most curious among you, we also have the option of prompting a specific failure. Let's now dive into the Manot solution that pioneers in filling the gap between product and development sides, as well as provide actionable insights about the model performance, helping reduce costs on model and data curation. I'm going to show an example of a model, background removal, and we will see how Manot generates failure examples, images, where that background removal will fail, having only a set of images and the model's output on it. For the demo purposes, we have used ISNet to train it for a background removal task on the DIS 5K dataset. The training was done on around 3,000 images, and the test set had around 500 images. And the mean intersection over union was around 82%. If you log into our platform, you will see a couple of public demo examples, and one of them is this. In this example, Manot generates insights in the form of 40 images that the model will potentially fail to accurately remove backgrounds in. The failure images are clustered by similarity, and the user has control over the number of clusters over here. And here we see some examples of images that the model will fail on. In this cluster, we can see that Manot is telling us there is a set of images with green glasses on a table. We can further infer that the problem here is likely that the glasses are blended in with the table and the model is failing to accurately identify and remove the background. And one of the key features of Manot is an importance score over here, which is provided for each image or the cluster. And the higher score is the worse the model will perform on this data sample. The impact is scored out of 10, and the higher the number, the more likely it is to be a problematic scenario for the model. So this is Manot. We hope our platform will enable product and development teams to communicate in a more efficient way and refine and redeploy models more quickly. Thanks for being part of this learning experience. I highly encourage you to check out the platform for yourself. For sure, drop us a line if you have any questions or suggestions. And remember, we are here to make sure the platform serves your benefits and needs. Thank you.